Hello, this video presents our final project for 6881, Robotic Manipulation. In our project, we explore how interaction can be leveraged to augment the scene perception task. In particular, we apply simple geometry-based approaches that would usually perform poorly in cluttered scenes with completely unknown objects, and show that these methods can yield good scene segmentation and object model discovery performance when combined with deliberate physical perturbations to the scene. Our experiments are run in a cluttered environment generated by dropping 15 objects onto the work surface. The initial type and location of the individual objects is randomized to ensure a wide variety of cluttered scenes. Next, we will provide an overview of our interactive segmentation system. First, we describe how the environment is set up.
So the manipulation station here represents the environment in which the robot arm, gripper, work surface, and all cluttered objects are present. Additionally, there are 6 depth cameras placed in the scene and in simulation and in the equivalent physical setup. This gives us access to various point clouds of the scene as well as the state of the robot, for example, its joint angles. We can merge and downsample all the point clouds obtained from multiple cameras to obtain a single point cloud containing a good view of the combined scene. Since we know the state of the manipulation station, we can set up a separate renderer that allows us to see what the manipulation station would look like without any of the clutter. We use this renderer to render a point cloud that is equivalent to the point cloud obtained from the real cameras, but does not contain the arm, gripper, and the work surface. Here are some examples of the point clouds obtained from the manipulation station and from the simulated renderer. With these 2 point clouds, we can easily subtract out all the points that are due to the arm, gripper, and work surface, leaving us only with points that are due to unknown objects of interest.
Our approach for detecting changes in the scene relies on comparison of temporally consecutive snapshots of the object-only point cloud. For this purpose, we obtain a once delayed and a twice delayed copy of the input point cloud. Given these 3 point clouds representing consecutive snapshots in time, we calculate the difference between each pair of consecutive point clouds. This allows us to obtain 2 new point clouds containing only the parts of the scene that have changed. With these 2 point clouds containing only changes in the scene, we now attempt to find a rigid transform describing the motion from the first change to the second change. We use an iterative closest point algorithm to find such a transform. Sometimes a change to the scene is due to the motion of a single object. Then it is possible to accurately describe the motion using a single rigid transform. ICP reliably finds a transform that registers the green point cloud to the red point cloud with very high accuracy. However, in other cases, multiple objects may be moving. Except in rare cases where a stack of multiple objects is moving, this motion cannot be described with a single rigid transform. Therefore, the transformation returned by ICP will yield a poor quality registration, as detected by a high mean squared distance between corresponding points. We use this metric to identify cases where we were not able to successfully isolate an object.
To introduce these deliberate perturbations into the scene, a simple task-level controller to plan the pushing maneuvers is implemented as a state machine, which controls the trajectory generation and following behavior, accounting for both unexpected collisions, successful interactions with the target, and successful isolations of a single object. After a successful push, or when an unexpected collision or other failure might occur, we make sure to retract the arm away from the pushing target and get ready to repeat the entire process. The second part of the task level controller is the trajectory generator, where we generate trajectories that push our targets. These are generated using a simple random sampling-based approach, which require only an input point cloud. No normal information is required, and no assumptions about the geometry of the point cloud are made other than the availability of a bounding box describing the allowable working area in which the clutter is located. First, a line is generated that traverses the workspace with a randomly sampled orientation and position. Next, we check if the line intersects the point cloud by going along the line until a point in the point cloud is found to be the closest to the current position along that line. By starting collision checking along the line from outside the workspace going inwards, we ensure that we do not plan motions that would begin on the inside of objects in the workspace, and ensure there is enough space for the gripper to approach the object without needing normal information. We then prepare a trajectory that connects the current position of the gripper with the target location. Finally, we attempt to find a joint space trajectory to follow this plan. We accomplish this by solving for a series of optimization problems along the plan. If this process is successful, we execute the trajectory under supervision of the state machine, which will abort execution as necessary.
The previously discussed components are connected to form the overall system architecture shown here. Next, we show our system's output after being run on several clutter scenarios. These results show the point clouds recognized by our system. Since our algorithm naturally results in the robot decluttering the scene, most point clouds represent a relatively complete view of the object. About 85% of the recognized point clouds correctly correspond to a single object. In the remaining cases, the robot executed a push that moved multiple objects simultaneously, but the objects moved as a single unit according to the same rigid transform.